the term here is u infinity du infinity by dx. I'm not getting that.
Okay, that particular displacement thickness. So what exactly you are not getting is that you are not able to convert the equation in the form of displacement thickness, right?
Yes.
Okay, so I'll try to derive it from the beginning. So you can take a look. And if it satisfies, you can tell me. Otherwise, you can tell me what exactly your problem is. Stop. Stop sharing. Stop sharing. So the integral equation for the momentum derived from the momentum equation. So I'll not go from the beginning. I'll take the intermediate step and then try to convert from there to the momentum thickness and displacement thickness. Okay. So I'll take from the final form of the momentum equation. So the general form of momentum equation will be d by dx of integral 0 to y u into u infinity minus u into dy is equal to 1 by rho into y dp infinity by dx plus kinematic viscosity into du by dy at 0 plus du infinity divided by dx 0 to y u dy. So this is the general form of integral equation, and we do not know the value of dp infinity by dx. So that will become for the case of flow or a flat plate from the momentum equation for the flow in the free stream, we can write it as this particular term. There is no variation of u in the y direction in the free stream, and correspondingly, the v stream v direction velocity will also be 0 in the free stream. So this particular term will be equal to 0, and then this will become dp infinity by dx, and this the y direction velocity will be 0 in the free stream, so that will also be equal to 0. So effectively, what you can get is this will become u infinity. If you give one, there was a small correction, dou u by dou x. So this will become u infinity dou u infinity by dou x. So what you can get is that u infinity dou u infinity, it will become in fact du infinity by dx is equal to minus of 1 by rho dp infinity by dx. So if you denote it by 1, this will become 2. Substitute this value into into 1. So 2 in 1, you get d by dx of 0 to y u into u infinity u into du minus of, this will become minus of u infinity du infinity by dx into y plus nu into dou u 0 by dou u 0 by dou u by dou y at y is equal to 0 plus du infinity divided by dx 0 to y u dy. So in this one, we take the u infinity outside, and we can try to represent in the form of momentum thickness. So that will be d by dx of u infinity squared 0 to y u by u infinity minus u by u infinity the whole square of dy is equal to du infinity by dx. You take this particular term on the right hand side, nu into dou u by dou y, that will be equal to shear stress divided by rho. So shear stress is equal to at the wall, shear stress at the wall will be equal to the mu, the dynamic viscosity mu into dou u by dou y at y is equal to 0. So this is kinematic viscosity, and we write in the form of tau w by rho. And this term will be having a dou u infinity by dou x. This term also will be having a dou u infinity by dou x, and we club them together. So and so that will be giving us dou u infinity by dou x minus of u infinity by plus the integral of 0 to y u dy. So this particular term, this y can be represented as in integral of 0 to y 1 dy. So this y can be written as integral of, that's a manipulation that we do, 0 to y 1 dy. So effectively the right hand side will become du infinity by dx into minus of u infinity integral of 0 to y 1 dy plus integral of 0 to y u dy. So what we do is that you will take u infinity outside on the right hand side. So when we take the u infinity term on the right hand side out, so this there is the additional shear stress by rho term also there. So it will be so rho by rho. So the RHS will become equal to root of tau rho by rho plus du infinity. I'm just writing the same thing on the right hand side to make it easy for me. Du infinity by dx minus u infinity integral of 0 to 1 1 dy plus integral of u dy plus integral of 0 to 0 to y u dy. So we take the u infinity term outside as common. That will become tau rho by rho plus du infinity by dx into u infinity is equal to integral of 0 to y u by u infinity. When we take the u infinity out of it, so this right hand side, this will become u by u infinity, and dy can take it outside. This will become you take the u infinity out, so taking minus inside, so it will be u by u infinity minus 1 into dy. And the LHS is the same. That will be d by dx of u infinity squared into 0 to y u by u infinity. When we take the u by u infinity term outside, u by infinity into 1 by the u by u infinity, u by u infinity into dy is equal to tau rho by rho plus du infinity by dx into u infinity multiplied by 0 to y u by u infinity minus y dy. So take this term on the left hand side. So this corresponds to momentum thickness momentum thickness. So that will be d by dx of u infinity squared. Momentum thickness, we can denote it by delta 2. And this will become, so when we take it to the left hand side, this will become plus du infinity by dx u infinity into 0 to y into 1 minus u by u infinity dy. That will be equal to tau rho by rho density. So omega divided by rho. So this term integral 0 to 0 to y into 1 minus u by 1 minus u by u infinity dy. This is called displacement thickness delta 1. So this corresponds to momentum balance. No, this corresponds to the mass balance that happens between two same y unit from the that is far away from the surface. And delta 2 corresponds to the momentum balance between two vertical heights of y that is far away from the wall. So you can write it in the form of d by dx u infinity square delta 2 plus u infinity du infinity by dx into delta 1 is equal to tau rho by rho. So this corresponds to the final general form of momentum equation. In the integral. So I guess that's it. So
Can you go to the last page?
yeah. Yeah.
The last term in the first equation.
Last term in the first equation, this equation.
Yes. Where
Uh,
it is coming from? I mean,
these,
the derivation that sir has done, that term is not there.
can you please write it on the chat box? Your voice is slightly disturbing.
Okay. Okay.
Okay. So for that we should go further back. So I'll try to explain that as well. So for that I'll start from the beginning. Then only I guess it will be clear. So your doubt is about. No, I understood. I understood. So I can actually derive it here. So I can actually derive it here. So your doubt comes where this equation is coming from, right? So the right hand, this particular term in the equation is coming from. So I'll start deriving it from the basics. Then and I'll try to arrive at this equation. And then from further onwards, it's the same. So if you arrive at this equation from there onwards, we can follow the same methodology that I have just now discussed. So I'll try to discuss regarding how to arrive at that particular equation, equation number 1. So the continuity equation. So the main 3 governing equations will be continuity equation. So for the time being, we just take the 2 governing equations, continuity equation dou u by dou x plus dou v by dou y equal to 0. And then differential form of the momentum equation in the x direction. The general form that will be. What we could do is that u dou u by dou x plus v dou u by dou y is equal to minus 1 by rho dou p by dou x plus mu dou square u divided by dou y squared. So can you please mute yourself so that you can actually.
Yeah, sorry, sir.
Yeah. So this is a general form of the general differential form of the momentum equation. So what we could do is that we could do a mathematical manipulation. So we multiply this continuity equation by u and add with the 2. So we'll get 1 plus 2. We'll give 2u dou u by dou x plus u dou v by dou y plus u dou v by dou y plus v dou u by dou y equal to minus 1 by rho dou p by dou x plus mu dou square u divided by dou y squared. So this will be the same as dou u squared divided by dou x plus this will be dou uv divided by dou y is equal to minus 1 by rho dou p by dou x plus mu dou square u divided by dou y squared. So this will be the momentum equation in the by including the continuity equation also. So this is a general form of the momentum equation in the x direction by doing this mathematical manipulation. We could do this because the right hand side of this particular term is 0. So you multiply this equation by u, the whole term still remains a 0. And if you are adding that particular equation to this equation, the actual value won't be changing. So this is basically a mathematical manipulation that we are doing. So now what we could do is that we could integrate these equations from one point to the another. To arrive at the integral form of the momentum equation, so what we could do is that we integrate it from 0 to y. So integrate 3 from 0 to y. So what we would get is integral 0 to y dou by dou x u squared dy. Similarly, the y differential also dou uv by dou y dy equal to minus of 0 to y minus of 1 by rho dp. This particular term will be equal to so if this is a flow over a flat plate, so what we could see from the initial analysis was that we have represented dou p by dou infinity as dou p infinity by dou. So in the previous discussion, what we have seen was that this dou p by dou x, right? So we have written it in the form of dou p infinity by dou x, right? So you could write it straight away since this is a flat plate. So what happens is that in the case of a flat plate boundary layer, from the case of a scaling analysis, what we could say is that the pressure at this particular point will be same at these 2 points. So if you take a dou P by dou X pressure gradient in this direction, that will be same in this direction as well. So this is from the scaling analysis between dou P by dou X and dou P by dou Y that we have seen in one of the earlier lectures. So by taking boundary layer theory is applicable when the boundary layer thickness delta is very much less than that of the plate length. This delta is very much less than that of the plate length L. So using this and the scaling analysis, what we could prove is that dou P by dou X is very much greater than dou P by dou Y. So that means that the Y direction pressure gradient across the boundary layer will be 0. So that corresponds to only pressure gradient in the X direction. So this flow direction is X direction. So and this direction is Y direction. So what we could say is that dou P by dou X will be greater than dou P by dou Y, and that means that the pressure difference in this line will be same as that of the pressure difference this line. So this is a free stream where the pressure difference will be dou P infinity by dou X, and the same the pressure gradient will be felt here as well inside the boundary layer as well. So that's how we could write this as dou P infinity by dou X dy plus integral of 0 to y mu dou square u divided by dou y squared into dy. We can denote it at 4. So able to understand this? Why
Yes,
we have, yeah, okay. Yeah, then we can proceed further. Similarly, we have to do the integration for the continuity equation as well. From 0 to y, we integrate it. Integrate the 1 from 0 to y. So it will be 0 to y dou u by dou x dy plus 0 to y dou u by dou y dy. So equal to 0. So that gives integral of 0 to y dou u by dou x dy plus this is dou v by dou y. So the dou v by dou y into dy, that will be v at y v by 0 equal to 0. So this will be Vy minus V at surface will be equal to 0 for no slip condition and impermeable wall. So so that will be Vy minus 0 is 0. That will be the final integrated value for this second term. The first term. So this is actually a mathematical manipulation that we do to calculate the value of Vy. So what we could do is that it will be Vy is equal to so for an impermeable, so make sure that it's an impermeable wall, then only we can write V of 0 is equal to 0 at the surface. So no suction and no blowing happens. So Vy is equal to minus of integral 0 to y dou u by dou x into dy. We can write it like this. Fine. So continuing with the analysis for the equation 4. Therefore, equation 4 will become so the first term will be integration of the differential. So we have to integrate this differential. So by applying the Leibniz rule, that converts the integration of differential to differentiation of an integral, and correspondingly, what we could write is that we do not know the value where exactly the point y is. If you take the y somewhere inside the boundary layer or nearby the boundary layer, we can't actually predict whether the y direction velocity will be there or not. So that's why we say that the boundary layer is not a streamline, right? So there will be flow across the boundary layer. So once the flow across the boundary layer happens, you can't consider it to be a streamline. So if the flow, if there is a flow across the boundary layer, that means that there is a y direction velocity as well. So we can't actually put the Vy is equal to 0. That's not a boundary condition. So basically what happens is that this is a streamline. This is a boundary layer, right? So the layer will be going like this. So the if do you know what is streamline? So streamline corresponds to a line which will be the end of flow. So the basic definition of the streamline is that there will not be any flow across the streamline. So the tangent to the streamline will give you the actual velocity. But in the case of boundary layer, if you consider this to be the boundary layer, so this is not a streamline because there will be variation of velocity in both the y direction as well as x direction. So this is u and this is v. So you can easily prove that because take a rectangle the cross section. So maybe a cuboid that extends into the plane of the paper. So whatever. So if this is the flow rate in this direction, if you come here, the flow rate will not be the same because here there will be a gradient in the u direction velocity. So by the time it reaches the end of the streamline, the rho u into the mass flow rate due to the x direction velocity, that will not be the same. So where will the extra mass flow rate will be going? So that means that the actual surface has to be curved. That will take into account the loss in the flow rate that happens in the y direction. So for that to happen, there should be a flow in this direction as well, right? So the velocity should slightly tilt upwards. So if that happens, so in addition to the x direction velocity, there should be a y direction velocity as well. This is because streamline is not a, as this is because boundary layer is not a streamline. So basically the definition of displacement thickness. So the displacement thickness from here will not be the same as that of displacement thickness here. So it will be slightly tilted upwards to take into account the loss in mass flow rate. So the same mass flow rate will be felt at a higher distance from away from the ball. And for that to happen, there should be a y direction velocity across the streamline. So that's why we say that the v direction velocity is not zero at the boundary layer, and hence it's not a streamline. There will be flow across the boundary layer. Yeah, so that is done. So that's why v of y is not zero. So in order to calculate v of y, we have actually done this integral equation of the continuity, and we have obtained vy in terms of this form. And then we will require that once we do the integration of this equation 4. We apply the Leibniz rule for converting an integral of differential to a differential of integral. So that will become dou by dou x of integral of 0 to y u squared dy. And then we have to check the value of the integrand. So this will be having a plus u squared at y is equal to y, and uh, this one will be u squared at y is equal to 0. So the value of this particular term, okay, Okay, Vicky, but there's a small correction. So so this will become so Leibniz theorem is actually used to convert integral of a derivative to a derivative of the integral. So the first term equation for first term will become integral of 0 to y d dou by dou x of u squared dy will become equal to d by dx of integral of 0 to y u squared dy plus the bottom substitute u squared at 0 multiplied by d by dx of 0 minus of u squared at y multiplied by d by dx of y. So u squared of 0 will be equal to 0, and this will be equal to 0. And this we are keeping a y constant. That's why u squared of a y into dy by dx will be equal to 0. This particular term is equal to 0 because we are actually fixing the value of y to be some height from the x. That's why the variation of y with respect to x direction will be a the y will be a constant with respect to x, and the variation of a y with respect to x equal to 0. That's why you could write the first term is equal to the integral of the derivative will be equal to derivative of the integral. So the first term will be straightforward, and the second term, equation 4, second term will become integral of 0 to y dou u v divided by dou u. So that's very straightforward. It's integration with respect to y, but there it was an integration with respect to y and differentiation with respect to x. We didn't have an option. Here it's straightforward. That will become uv or y minus of uv at 0. So uv at y will be equal to u infinity. V at y will be equal to we do not know what will be the y. So therefore we write it as uy vy, and u at 0 is equal to 0, v at 0 is equal to 0 because of impermeable wall. The u is no slip condition, so that will be equal to 0. Therefore uy vy. So this vy is an unknown. So we will get this vy from the integral form of the continuity equation. So that's why we have actually determined the value in the equation 5. And on the right hand side of the equation 4, we have to integrate minus of 1 by rho dou p infinity by dou x into dy. And so here the dou dp infinity by dx is independent of y. So at this particular point, as we have seen, inside the boundary layer and outside the boundary layer, the pressure will not vary along the y direction. Therefore, what we could see is that so we can take the dp infinity by dx outside the integral because that is a constant with respect to y. So equation 4 third term will become dp infinity by dx minus of 1 by rho into y. And then of 0 to y dou p by dp infinity by dx dy equal to dp infinity 1 by rho dp infinity into capital Y. So only the term that will be remaining inside the integral will be 1. So the one integral of 0 to y of 1 will be equal to y. 0 to y or 1 dy will be equal to y. And fourth term will be this term that you need to integrate, but the derivative is of y, and the right hand side the integration is also with respect to y. So it's straightforward. Equation for the term will become equal to 0 to y mu dou squared u divided by dou y squared dy is equal to, take mu outside, will be dou u by dou y at y minus mu dou u by dou y at y is equal to 0. So if you take the boundary layer, if you take this y outside the boundary layer, immediately outside the boundary layer, the variation of the velocity with respect to y will be equal to 0. So this particular term will be equal to 0. And this particular term is not 0 because this corresponds to the shear stress. So from this, we can actually get the shear stress value. And solving, taking all these four, we can substitute in the equation to get the simplified value of the integral form of a momentum equation. So it will be dou by dou x of integral of 0 to y u square dy plus uy vy will become uy into the integral form of a vy. So that will be minus of dy dx. From this one, it will be minus of dy minus of dou by dou x of u dou u by dou y. So just like the previous case, this will be integral of the derivative. So the final form will become, it will be dou by dou x of integral of 0 to y u dy at top minus is there. So this particular term will be a minus term. Then just like this integration, we have to use a Leibniz theorem. So that will be u into dou u into there's a minus here as well. So that will become minus of u into dou 0 by dou x, that will be 0 constant. So dou 0 by dou x, that will be 0. On the top side, it will be minus of so u0, and here it will be u y and dy by dx. Uy by d and dy by dx when it is a constant, so that will be equal to 0. Therefore, we could write vy is equal to minus of this one will be same as sort of this. So you can take the integral inside and take the derivative outside. So that will be minus of dy by dx of integral of 0 to y u dy equal to right hand side will be equal to minus of 1 by rho dp into dy, this term, and then this term as well. So that will be minus of nu dou u by dou y at y is equal to 0. So you have dou by dou x of this particular term. So this is u y when it is away from the wall, much beyond the boundary layer. You can write uy is equal to u infinity. So you can substitute that here. So we do some kind of manipulations here. So this one u infinity can go inside since it's a constant. So left hand side will become dou by dou x of integral of 0 u square dy minus of integral of 0 to dou by dou x of 0 to y u infinity u dy is equal to minus of rho dp infinity by dx y minus mu dou u by dou y at y is equal to 0. So this term can couple it together. So it will become integral of 0 to y uh, and taking a negative, multiplying this term by negative, it can be u infinity u minus u square dy is equal to minus here 1 by rho dt infinity by dx y plus mu du by dy at y is equal to 0. So this will become, and we take the u value outside, we'll get this form straight away. So it will be dou by dou x of integral of 0 to y u infinity u into it will be u into u infinity minus u into d by is equal to 1 by rho y dou p infinity by dou x plus mu dou u by dou y at y is equal to 0. So then what we can do is that we can do some kind of a manipulation to u infinity u into u infinity minus u in both terms. Yeah, there is some slight correction. Can actually do this because this was uy u infinity. So I made a small mistake here. So in from this step, so in this step, we have seen uy is equal to, we have put this is equal to u infinity. But the issue with this kind of an analysis is u infinity, though doesn't vary with respect to y, it can vary with respect to x. So if you assume that it's a flat plate, okay, it doesn't vary with respect to x direction. But if you assume it's a flow through a tube, u infinity will become the core velocity. So that can vary. So you can't directly take it inside this particular derivative d by dx. So you have to do some kind of a manipulation to actually find out the value. So I guess that is where the additional term on the right hand side, the third term on the right hand side will come into picture. So what happens is that this is not right. You can't take it straight away. So you have to do a bit of manipulation to arrive at that particular value. So I had assumed that this u infinity is independent of x, but that's not the case. So what we could do is that we can write for this we do a manipulation. So what we need is the value of uh, uh, we need to put this u infinity inside this d by dx so that those two terms can be clubbed together. The first and the second term can be clubbed together, but it's not straightforward. So what we do is that we take the derivative dy dx of u infinity u integral of 0 to y du y. So this could be written as this could be written as the so this is same as that of minus of, if you take this d by dx inside also, it will be the same. So what we could say, u by ui, we have seen the integration, Leibniz rule. So it will be d by dx of u infinity u and dy. So that will become, applying the chain rule. So it will be u infinity dy. So u infinity is independent of y. So that is u infinity take out. So it will be 0 to y d by dx of u dy plus integral of 0 to y, and then that will be the u of du infinity by dx into dy. So what this term is integral or derivative, so that it can be taken inside. So it could be written as so what could be written as, so this could be written as the in the same way as that of the previous case, to put it in the to the d by dx term. So derivative outside and doing the integral. So it can follow any order. Just now we have seen the Leibniz theorem, where the second and third term of the Leibniz rule will become equal to 0, because the y is a constant, and 0 is also a constant. So you can take it outside as well. So you can write it as u infinity d by dx of u infinity d by dx of 0 to y 0 to y u dy, and you can actually plus this du by infinity by dx is independent of y. You can write the du infinity by dx integral of 0 to y u dy. So the second term, uy into minus of d by dx into u infinity into minus of d by dx of integral of 0 to y u dy. This will be same as that of the second term in the picture. So in order to get, so this can be substituted as u infinity d by dx of 0 to y u dy can be substituted as d by dx of integral of 0 to y u infinity u dy. Yeah, that's what I was about to, I was discussing, right? So it's a Leibniz rule. No, that's what I was trying to discuss. So there is this Leibniz rule that we have to follow. This is the Leibniz rule. So what we do is that if you want to calculate an integral or derivative, that will be equal to derivative of the integral plus the value u squared, the inside value, this particular value at the upper limit of at the lower limit, u squared of lower limit multiplied by the derivative of the lower limit constant. So d0 by dx minus the value of u squared at y, that is upper limit, multiplied by the derivative of dou y by dou x. So in this case, since the integration is from 0 to y, what happens is that this constant d0 by dx will become equal to 0. Similarly, y is a constant with respect to x, so we can write dy by dx equal to 0. So that's for this particular case, since we are keeping the bottom and the top part of the integration constant, these two terms will become equal to 0, and integral or derivative will be equal to derivative of the integral. That's why we could write integral of derivative equal to derivative of integral, because yeah, that's Leibniz rule. Yeah, then so the second term u infinity d by dx could be written as d by dx of first term of this one minus of this term. du infinity by dx integral of 0 to u dy. So we can denote it by another equation. So this can be denoted as maybe 5, no 6, 5, 6. This can be denoted as 6, and this can be denoted as 7. Therefore, the second term, this particular term, uy minus dou by dou x of integral 0 to y u dy, could be written as uy is same. When y is away from the wall, it will become equal to the free stream velocity. So u infinity dou by dou x of this one will be equal to these subtraction of these two terms. So substituting this here, it will become the first term same integral 0 to y u square dy, integral of 0 to y u square dy, and the second term will be plus of this is minus also is there. So this will become minus of this one plus plus of this one. So it will become minus of d by dx 0 to y u infinity u dy plus du infinity by dx into 0 to y u dy. So when we substitute that, it will become equal to right hand side, it will be minus of 1 by rho dp infinity by dxy minus mu dou u divided by dou a at y is equal to 0. So clubbing these two together, that will be dou by d by dx of integral of y, and taking a whole negative for this term. So multiplying with this one, so it will be u infinity u u into u infinity minus u into dy equal to 1 by rho dp infinity by dx into y plus mu into du by dy at y is equal to 0. And we multiply this particular term by a negative and take it on the right hand side. So that will become positive of du infinity by dx u dy integral of 0 to y u dy. So which is the same as that of this equation. This is the same equation from where we started today first. So the additional term du infinity by dx, du additional term, the only additional term that comes into picture is du infinity by dx into integral of 0 to u dy. So you could actually take it inside, because this is independent of y direction. So du infinity by dx is independent of y direction. It's actually a constant. It's actually a constant. So it could be written as, the whole term could be written as 0 to y u du infinity by dx, constant with respect to y. So that's why you can take this inside, and that will become the same as that of the first equation that we have discussed today. So the first equation is du, the term is du infinity dx integral of u dy. So I'm just renumbering the rest of the things. So it will be 9 in 8. Yeah, so I hope you understood how, okay, right. So we can actually move into today's session. So very warm good afternoon to one and all. Welcome to the 7th week tutorial session of NPTEL course Convective Heat Transfer. My name is Ananthakrishnan. I'm a Ph.D. scholar from Department of Mechanical Engineering, IIT Delhi. So in this week, we will see a few problems based on the external natural convection, few theoretical and derivation based problem, and numerical based problems based on external natural convection. So without wasting much time, we can move into the problem straight away. Look into the problem and try to solve it. I'll also try to solve it within a couple of minutes. Yeah. So this is a problem on integral solution for natural convection. The temperature profile is given, velocity profile is given. We need to actually we need to it's given that the boundary layer thickness, hydrodynamic as well as the thermal boundary layer thickness are the same, and we need to determine the Nusselt number that is given by this formula. So this follows the same integral solution approach as that of the normal force convection approach, apart from except from the fact that there is one additional term that will come into picture because of the free convection term, that is with respect to the buoyancy term. So we can directly take it from the integral form of the momentum equation that was discussed in the lecture. And from there, we try to solve it and substitute these velocity profiles, arrive at the final solution, and then they integrate by using the general velocity profile variation with respect to y. So in this case, the x direction, if this is the vertical wall, x direction will be this. So this will be the y direction, and this will be the x direction. So the it's kind of different from that of the previous force conversion. So the vertical dimensions away from the wall will be x, and the flow direction will be y. So what we could see is that the thermal boundary layer will be same as that of the hydrodynamic boundary layer, delta equal to delta T. So we can what we can do is that we can directly take the integral form of the momentum equation. So that will be d by dy. So this is the final this particular form that we are using is the equation that we obtained after doing the initial manipulations and reductions. So this is the final form of the integral momentum equation. So that will be 0 to here the vertical dimension will be x, somewhere far away from the wall, x 0 to x v squared dx is equal to minus of nu dou v by dou x at x equal to 0 plus g beta, that additional term that comes in the picture due to the buoyancy. Integrated from 0 to x t minus t infinity dx. So what we could do is that we can substitute the given velocity profiles in this equation. So we actually try to reduce it. So we can write it as the v can be written as this particular v. This v doesn't have, we have to actually scale this velocity v. So that can be scaled with respect to the longitudinal dimensions along the y. So from the scaling analysis in the previous week's lecture, what we could see is that v is actually v can be actually scaled with respect to y. So it's a square root function. So v can be scaled as a constant multiplied by the y raised to 1 by 2. So that is a scale that we could use to actually convert this particular constant into some other form. As you could see in the final Nusselt number, there is no value of the v as such straight away. So we have to have some kind of control over it. So for that, we use this particular scaling analysis based answer that we have obtained in the previous from the previous week's lecture. Week 6 lecture. So v is equal to cv raised to y by 2. Similarly, the boundary layer also would write it as c raised to some other constant So you can denote by delta and raise to 1 by 4. We will keep it aside for the time being. This is something that we can obtain from the scaling analysis. So if you we are not going to directly use it as of now, but we just it should be there in the back of the mind, so that at a later stage when some particular constants are to be determined, we can make use of these two equations. So it can be denoted as A and P. So this equation actually has three parts. One is this the direct this is a viscosity part, and this is the inertia part, and then this is the buoyancy related part. So we have seen how to obtain the v square term. So you actually add the continuity equation by multiplying the v term into it, and then add it with the momentum equation to arrive at this equation. Then you integrate and derive this form. That's why the square term comes into picture. And then there is this is a viscosity term and this is a buoyancy term that is unique to the natural convection. So the momentum equation will be having three parts. Now what comes into picture is how to substitute the value of the velocity profile that is given. So in this form, it can become quite complicated. So you can denote x by delta is equal to, we can call it by m. So this will become v into m into 1 minus m the whole square. And similarly, this will become t minus t infinity is equal to delta t into 1 minus m the whole square. So we can substitute that straight away. It will become this is small v is equal to capital V into m into 1 minus m squared. So m squared will be there. So it will become capital V squared d by dy of 0 to x. So x can be written as, so if x is equal to m delta, dx can be written as delta into dm. And when x varies from 0 to x, the value of m varies from 0 to x by m. The value of the velocity further away from the thermal boundary layer or the hydrodynamic boundary layer will be 0, because the ambient will be 0. This is the free conversion case. So therefore, the reduction 0 to x can be reduced to 0 to delta. So this will become 0 to delta by m, and the scaling happens 0 to x by 0 to x by delta. So it will be delta by delta. That will become, the integration is from 0 to 1. So we can change the limit once we give the similarity variable, that will become 0 to 1. Dx will become delta into dm. So delta, take it out. And v squared will become equal to, we have taken the constant, this v squared away, the scaling factor away, and then the inside it will be m squared into 1 minus m raised to 4 dm equal to and dou v by dou x at x equal to 0 will become equal to, it can be scaled as mu into v divided by so what we do is that we just differentiate v with respect to x, and then put x equal to 0, and we'll get the form of v by delta. By applying the chain rule, we can substitute and we arrive at this value. And then similarly, this will become g b delta, g beta g beta so it forgot one terms of dy by d, okay, d by dy. It will become g beta, and t minus t infinity will become equal to delta t into 1 minus m squared. So that will be g beta delta t and dx could be written as m into dm into dm into delta. So delta also outside as the limit changes from 0 to 1 and 1 minus m the whole square dm. So we have to integrate this particular term from 0 to 1 and this particular term from 0 to 1. So the solution for this will become equal to 1 by 0.5 after integrating, and this one will become equal to 1 by 3. So final solution, the final differential equation, simplified form of differential equation will become d by dy of v squared we can actually take the v squared into delta inverse inside the y. So v squared delta divided by 105. We keep the small correction. So I had put the d by dy inside, so it should be outside. That was a mistake which I had done in the previous step. So yeah, it should be d by dy outside. So it will be d by dy of v squared delta divided by 105 is equal to minus of mu v by delta plus 1 by 3 into delta t delta g beta. So we can denote this by equation A. So this is the final simplified form of the momentum equation. And now we can actually look into the energy equation. So energy equation is kind of same as that of the previous analysis. It will be d by dy of 0 to x vt infinity minus t dx equal to alpha dou by dou x at x equal to 0. This is also obtained as part of the scaling from the integral analysis, basic integral analysis in this week's lectures. So we substituted the similarity profile in this one and obtained the values as such. So it will become d by dy, just like the previous case, it will be integral of 0 to x, v into t infinity minus dx will become minus of v delta t delta into 0 to m into 1 minus m raised to 4 dx. It's a temperature profile. It will be 1 minus m squared. Then there is v velocity, that is m into 1 minus m squared. So it will become, multiply both of them, it will become m into 1 minus m raised to 4 dx. That is equal to this particular term. Differentiate the velocity profile, temperature profile with respect to x, and substitute, put x equal to 0. We'll get is equal to minus of 2 alpha delta t divided by delta. So therefore, what we get is that d by d. So what we could do is that this particular integral will be equal to 1 by 30 Yeah, so the reduced form of this equation will become d by dy v delta is equal to 60 by delta into alpha. So this could be written as b. So we have two reduced form of equations, one for the momentum equation and one for the energy equation. So we should try to solve this. So that involves the momentum equation involves V and delta. Those two are the unknowns. And similarly, this is capital V, not small v, it's capital V. So, and similarly, the thermal equation also, energy equation also involves V and delta. So, so this is not straightforward as like the force conversion where V, the reference velocity was the free stream velocity in terms of flow over a flat plate. Here, there is no reference velocity as such. We have to actually determine the value of V from some other analysis, and that will be obtained from the scaling analysis. So in the previous week's lectures, we have seen the scaling analysis, and here we have obtained a scale for V. So basically, V can be scaled as C into y raised to 1 by 2, and delta could be written as some other constant into y raised to 1 by 4. So we substitute both of them, make use of A, B. I use the wrong terminology again. So it will be should be C and should be C, it should be D. So put A and B in C and D. We can get V is equal to C V raised to 1 by 2, and delta is equal to C delta raised to 1 by 4 in C and D. We can obtain the value of the constants CV and C delta. So, and then doing a bit of mathematical manipulation, what we could obtain is the value of CV is equal to 5.17. It's a bit complicated in terms of Prandtl number. Prandtl number is mu by alpha. Prandtl number plus 20 by 21, the whole power minus 1 by 2. GB delta T divided by mu squared 1 by root is 1 by 2. So, and C delta is equal to 3.93 Prandtl number raised to minus 1 by 2. Prandtl number plus 20 by 21, the whole power 1 by 4. GB delta T divided by mu squared, the whole power minus 1 by 4. So these are the value of the constants that we could obtain by substituting the value of V and C in this one, and it will become this will become a function of only Y, and then we can get the value of CV from here straight away. And this will become a function of Y, and you can get the value of C delta from this one straight away. And substituting it back, so CV, we now have got the constants value of CV and C delta, and therefore delta could be written as CV into Y raised to 4. So C delta into y raised to 1 by 4. So delta is equal to C delta into y raised to 1 by 4. So that will be equal to 3.93 Prandtl number raised to minus 1 by 2. Prandtl number plus 20 by 21, the whole power 1 by 4. GV delta T divided by mu square minus 1 by raised to 4. Y raised to 1 by 4. So we do some kind of a manipulation. So we know that Rayleigh number is equal to Kirchhoff number into Prandtl number. So the Prandtl number term is there, and G with delta T. If you assume a Y value, so we can take the uh, Y value outside and do and calculate the value. So we have a Prandtl number, we have an equivalence of Kirchhoff number, and then we can obtain it in the form of Rayleigh number. So what we do is that this is GB delta T divided by nu square raised to minus 1 by 4. So we can actually multiply and divide it by y raised to minus 1 by 4. So can be minus 1 by 4. So this will become y raised to minus 2 by 4. It's effectively it's oh, I beg your pardon. So in order to take it, you have to actually have LC cube or y cube inside it. it would be better if we can represent, we can actually take the y outside. So I'll try to do that once. It's just for convenience that I'm trying to do it for convenience purpose. So it will be 20 by 21. We take Prandtl number out of it. It will become Prandtl number raised to 1 by, you take Prandtl number out of it, it will become Prandtl number raised to 1 by 4 into Prandtl number raised to minus 1 by 2. So it will become Prandtl number raised to minus 1 by 4. So Prandtl number, so it will become Prandtl number is equal to nu by alpha. The momentum diffusivity to thermal diffusivity. Then this will be Gb delta to G beta delta T divided by nu square raised to minus 1 by 4. And if you want to take divide it by y, you can actually divide and multiply and divide it by y. So take this y to the left hand side. So you can write, this is just a manipulation, mathematical manipulation of simplification of the problem. 3.93 and take the Prandtl number outside. So you'll get it in the form of Prandtl number raised to minus 1 by 4. And that extra terms will be 20 by 21. Prandtl number raised to 1 by 4. This will be nu raised to nu by alpha raised to minus 1 by 4. So it will be Gb delta T divided by nu squared into nu by alpha raised to minus 1 by 4. So it will be y raised to 1 by 4 minus minus 1. So it will be minus of 3 by 4. So take it up inside. So it will be 3.193 plus 20 by 21. Prandtl number raised to 1 by 4. Cancel this and this. So and take this y cube inside. So it will be G beta delta T y cube divided by nu alpha raised to minus 1 by 4. This is minus 3 by 4. When you take it inside, it will go on the top. 3 will go on the top and minus will remain here. So this will be equal to Rayleigh number, and it will be equal to 3.931 plus 20 by 21 Prandtl number raised to 1 by 4 Rayleigh number at y raised to minus 1 by 4. It's delta y. So you have an equation for delta as well here. Now, what we need is the Nusselt number. We need to prove that the Nusselt number obtained by the heat transfer coefficient into y by k follows this form. So what we could write is that Nusselt number is equal to heat flux divided by delta T y by k. So it will be equal to, yes, that will be minus of k dou T by dou y. Dou T, here it is x, that is a vertical direction with respect to the plane. The horizontal, the perpendicular to the plate. The dimension perpendicular to the plate at the wall surface x equal to 0 by delta T y by k. So we differentiate dt by dx with respect to dt t with respect to x and substitute that x is equal to 0. We will get y by delta. Beg your pardon, we'll get this particular term will be equal to 2 delta divided by 2 delta t divided by delta. So it will become minus of minus will become, so k gets cancelled. Minus of minus will become 2 and delta t gets delta t, and on top also there will be a delta t. Both of them will get cancelled. This particular term will be the same, minus 2 delta t divided by delta. Alpha will not be there. So it will be 2 into the y remains divided by delta. So basically what we did was that this will become equal to minus of 2 delta t divided by delta t will get cancelled, minus get cancelled, so remaining 2y by delta. That's the only term that will be remaining. So that will be equal to Nusselt number. So we know the value of y by delta. We have obtained just now the delta v by, it's an inverse of this one, so it will become equal to 2 divided by 3.93 20 by 21 by Prandtl number plus 1 raised to 1 by 4, and Rayleigh number will become go on the top. So effectively 2 by 3.93 will become equal to 0.508, 20 by 21, Prandtl number plus 1, the whole power minus 1, take it on the top, it will be minus 1 by 4, and Rayleigh number raised to 1 by 4. So that will be the value of the Nusselt number that we are asked to prove in this question. So what we did basically was that we had it was given in the problem the velocity profile and the temperature profile, and we had in our hand the integral form of the the integral form of momentum equation and integral form of energy equation that was derived in this week's lectures. And we have substituted the similarity profiles in the form of a third variable. So for easiness, so once we integrate it, we'll get uh, the simplified form of these equations. So these two simplified form of equations will be in the form of V and delta. So unlike the force convection where the reference velocity was the core velocity or the free stream velocity, here there is no reference scale for the velocity. For that, we have to actually do the scaling analysis that was done in the previous week's lecture. So from that scaling analysis, what we obtained was that velocity is a function of c y raised to 1 by 2, the square root of 1 by 2, and delta. For the free convection case, delta is a function of y raised to 1 by 4, but there will be two constants. So what we could do is that instead of this capital V, we substitute the value of these two, and delta also we substitute in terms of y, and we will get the equation in terms of y. Yeah, we'll get the equation, two equations in terms of y, and then we can find the constants CV and C delta, and therefore from that we get the value of delta. It's just substituting the constant back, and once we get the delta, we just do some kind of manipulations to put in the form of Rayleigh number, and then Nusselt number equation is given, and we substitute this q double dash t0 minus t infinity could be written in terms of k into delta t minus of k into delta t divided by delta x. Differentiation of t with respect to x is equal to 0 at the wall surface. So t temperature profile is already known, and we'll get in terms of delta, and we substitute the value of delta that we obtain, and that's an Nusselt number. 'Look into the second problem. 1.5 by 0.5 meter vertical wall of parallel picked water container is heated uniformly by an array of electrical strip heaters mounted on its back. The total heat transfer furnished by these heaters is 1000 watt. The water temperature is 25 degrees Celsius. Calculate the height average temperature of the heated surface. Later, verify that most of the boundary layer that rises along the surface is turbulent. Try to solve it, and I'll also try to solve it in a couple of minutes. So this problem is regarding a zero point 0.5 into 0.5 vertical wall of parallelepiped water container. Vertical surface, vertical wall with chips attached mounted on the back of it. The heat transfer to the water rate is given as 1000 watt, and the temperature of the fluid is 25 degrees Celsius, and the width and the height is given as 0.5. So since the water temperature is given as 25 degrees Celsius, we have to calculate the properties at filling temperature. So we take the filling temperature is equal to 30 degrees Celsius, assuming that the surface temperature is sufficiently higher than that of the filling temperature and water temperature, because we do not know it right now. So we calculate the Prandtl number at these temperatures 5.49 for water, and K is equal to 0.61 watt per meter Kelvin, and G beta divided by alpha nu is equal to 25130 centimeter cube Kelvin. So we calculate the Rayleigh number with the flux related Rayleigh number. Its formula is G beta alpha nu h raised to 4 Q wall divided by K. Q wall is equal to the heat transfer divided by the area for the heat transfer. So it is centimeter cube Kelvin. Heat transfer is 4000 because Q double dash is equal to Q divided by area, 1000 divided by 0.5 into 0.5. So it's 4000 divided by 0.61, and h raised to 4 is because in this unit is in centimeter cube, we calculate we write in the form of 50 50 centimeters or 0.5 meters is the height. So it will be 50 cube multiplied by 0.5. So this will be in centimeter cube and this will be in meter. And we'll get the value to be around 1.03 into 10 power 13. So we can assume this to be turbulent because the value of flux Rayleigh number greater than 10 power 13. So that will be turbulent or transition to turbulent. So that gives an approximate answer, but this is not the Rayleigh number. So the value of so what we are supposed to calculate is the height average temperature of the heated surface. For that, actually, we require the Nusselt number, height average temperature. So we know the water's temperature. So if you know, if you calculate the Nusselt number, from that we can get the temperature difference, average temperature difference between the surface as well as the surface as well as the water. So based on that, we can get the actual temperature. So we need to calculate the Nusselt number. So Nusselt number is given by, for this case, for vertical wall surface, it's neglecting the constant term, average Nusselt number with respect to height is 0.132 into Rayleigh number raised to 1 by 3. Then and there is an equation that corresponds to the Rayleigh number averaged, the Rayleigh number and the Rayleigh number for this is the Rayleigh number and the Rayleigh number corresponding to flux. Rayleigh number with respect to temperature. the relationship between the Rayleigh number with respect to flux and Rayleigh number with respect to the temperature and with respect to the flux is Nusselt number. So basically, Rayleigh number is equal to Rayleigh number with respect to temperature will be equal to Rayleigh number with respect to flux divided by Nusselt number, average Nusselt number. So basically, Nusselt number is Q double dash divided by delta T H K. So Rayleigh number with respect to the Rayleigh number with respect to flux will be having Q double delta T. So this particular term will be equal to G beta divided by alpha nu into Q double dash H raised to 4 divided by K, and this term will be equal to G beta alpha nu delta T H cube. So so what we do is that we so this is trying to bring an equivalence between the Rayleigh number based on the heat flux and the Rayleigh number based on the temperature. So if we calculate the Rayleigh number based on the heat flux, we can get the Rayleigh number based on the temperature based on these formulas. So for that, we require the Nusselt number value. If you know the Nusselt number value, we can directly get the Rayleigh number based on the temperature. So basically, when we take this delta T by H on the left hand side, then it will get cancelled and it will become H raised to 4, and Q bar by K get cancelled and H raised to 4 again. So trying to bring an equivalence. So we know that for vertical plate, vertical surface, the Nusselt number, overall Nusselt number value for a surface will be equal to 0.132 into Rayleigh number raised to 1 by 3. So based on this, the Rayleigh number can be calculated as substituting the value of Nusselt number Rayleigh number with respect to H is equal to Rayleigh number with respect to flux divided by 0.132 Rayleigh number raised to 1 by 3. So you get it as Nusselt number So here we know the value of RAH. So if we can calculate the value of so from here we can calculate the value of RAH. If we can calculate the value of RAH, then we can back substitute to give the value of Nusselt number. So it will be RAH raised to 4 by 3 equal to RAH divided by 0.132. So this will be RAH is equal to RAH divided by 0.132 raised to 3 by 4. 3 by 4. So this is RA star raised to 3 by 4 divided by 0.132. So this will be RIS. Therefore, Nusselt number H is equal to substituting the value 0.132 divided by 0.132 raised to 3 by 4 multiplied by RIS raised to 1 by 3 is equal to RIS star raised to 1 by 4. So that will be the value. So this will be equal to 0.132 raised to 1 by 4. That will be equal to 0.219 RAH star raised to 1 by 4. Substituting the value of RAH star, we'll get the value of Nusselt number. Average value of the Nusselt number with respect to the height is equal to 392.3 So this Nusselt number with respect to height is given as Q double dash divided by delta T h by K. From here, delta T could be written as average value of the delta T could be written as Q double dash divided by mu h into h by K. So this will be 1 by 392 into 4000 into 0.5 divided by 0.61 equal to 8.5 degrees Celsius. And by calculating the value of temperature of the surface, average temperature of the surface is equal to T volt plus delta T plus T water equal to 33. This is 20. This is 25. And this is 8.3. 33.4 degrees Celsius. So our assumption kind of holds true. So the film temperature, though it may not be 30, it will be 25 plus 33.4 by 2. It will be 20. It will be somewhere around 29.2. So we can actually do one more iteration to get the actual value of the surface, actual value of these properties, and arrive at a slightly more accurate value. So we check for the whether the flow is still turbulent. For that, we had an approximation with respect to the Rayleigh number, flux related Rayleigh number, that the value was greater than 10 power 13. But to make sure that the actual Rayleigh number is greater than 19, we calculate. So we actually calculate the value of the Grashof number to determine whether the flow is turbulent or not. So we check for the Grashof number delta for 10 power 9 value. Whether if it is greater than 10 power 9, we can say that this is a turbulent flow. So the value of Grashof number is equal to Rayleigh number divided by Prandtl number. So Rayleigh number is equal to here divided by Nusselt number divided by Prandtl number. This is with respect to flux Rayleigh number. So flux Rayleigh number is 1.03 into 10 power 13. Nusselt number is 392 and Prandtl number is 5.49. So the value will be 4.8 into 10 power 9. This is greater than 10 power 9 and the value is turbulent. So our initial assumption that the flow is turbulent based on the flux Rayleigh number is right actually. So in this problem, we have calculated the value of the surface. We need to determine the value of the Nusselt number. So and take the right correlation that corresponds between Nusselt number and the Rayleigh number to get the value of the temperature of the surface. Looking at the third problem. A long rectangular metallic blade has width h is equal to 4 centimeter and temperature Tw is equal to 40 degrees Celsius. It is surrounded on both sides by atmospheric air at T infinity equal to 20 degrees Celsius. The long side of the blade is always horizontal. Calculate the total heat transfer rate per unit of blade length when the short side of this rectangular shape H is A vertical and B inclined at 45 degrees Celsius relative to the verticals. Try to solve it, and I'll also try to solve it within a couple of minutes. So this problem is a vertical convection based for free convection based problem on top of vertical plates. A long rectangular metallic plate has width h is equal to 4 centimeters and wall temperature 40 degrees Celsius. It's surrounded on both sides by atmospheric air. T infinity is to 20 degrees Celsius. The long side of the blade is always horizontal. Calculate the total heat transfer per unit of blade length when the short side of its rectangular shape is vertical and inclined at 45 degree related to vertical. So basically, it has got two parts. First part, when the wall is vertical, the it's actually long side will be on the horizontal. So this is the vertical case, and the horizontal case will be slightly. So the wall temperature is 40 degrees Celsius. 40 degrees Celsius. Calculate the total heat transfer rate per unit. We have to calculate the total heat transfer per unit of blade length when the short side of its rectangular shape is. Yeah, we have to calculate it per unit length. With this is the length direction. So we have to take a unit length in this direction, as well as in this direction. So it's a unit length. And width of equal to 4 centimeters. So the height is equal to 4 centimeters. So this height is equal to 4 centimeters. So we need to calculate the value of total heat transfer. So for that, so the heat transfer will be equal to the heat transfer coefficient multiplied by 2 areas into the temperature difference between the surface and the wall. So in order to calculate the heat transfer coefficient, we require the Nusselt number, and the Nusselt number is actually a coefficient can be obtained with respect to with a coefficient with respect to Rayleigh number. So first of all, we calculate the relationship between the Nusselt number and the Rayleigh number can be obtained as a standard relation for vertical wall at a constant temperature. So write the correlation here. For laminar flow, the Nusselt number correlation will be with respect to for a Prandtl number, it's air. So Prandtl number can be approximately to 0.7. So we can obtain the value of the Nusselt number correlation straight away. For the film temperature, for a film temperature, 20 degree plus 40 by 2, it will be 30 degrees Celsius. 20 for the 20 for the air and the 40 for the wall surface. It will be 30 degrees Celsius. We can obtain the Prandtl number, that is 0.72. K is equal to 0.026, and C beta divided by alpha nu equal to 90.7 divided by centimeter Kelvin. So for vertical plate, for a height of 4 centimeters, Rayleigh number is given as G beta divided by alpha nu h cube into delta T, that is T mod minus T infinity. So this is 90.7 centimeter cube per Kelvin H is 4 centimeter cube, so 4 cube into TW minus T infinity, that is equal to 20. So the unit is 1.16 into 10 power 5. So this is a laminar flow. So the Nusselt number for the laminar case is equal to Nusselt number is equal to for the laminar free convection over vertical plate. Nusselt number will be given by 0.68 plus 0.515 Rayleigh number raised to 1 by 4. So the value here corresponds to 10.19. Substituting the value of Rayleigh number, we get it to 10.19. And the heat transfer coefficient will be given as this Nusselt number value, K divided by H. This is height. So that's 10.19 into 0.026 divided by 0.04. So that should be equal to 6.62 watt per meter squared Kelvin. So once you get the heat transfer coefficient, we can obtain the total heat transfer rate. So the total heat transfer rate will be equal to total heat transfer rate per unit length will be equal to heat transfer rate multiplied by the instead of area per unit length, that will be equal to 2 times the height multiplied by 1 into TW minus T infinity. So it is 6.62 into 2 into 0.04 into 20. So the value will be equal to 10.6 watt per meter. So that will be the total heat transfer rate per unit length for a vertical channel. So the second part of the question is regarding inclination. This plate will be inclined at 45 degrees related to the vertical. So in that case, we have to obtain the value of a Rayleigh number. So in that case, the buoyancy related force will be in a direction 45 degree respect to the normal case. So we have to actually substitute the value of the so G should be resolved into X and Y direction. So we have to take the value of G resolved along the length of the inclined plate. So what we do is that, so this is an inclined plate now. Inclined plate. This is a surface, and this will be at a 45 degree, towards with respect to the horizontal. So heat transfer happens between this side as well as this side. So the G component, G will be in this direction. So the component of a G in a direction 45 degree will be should be resolved perpendicular as well as along the plate. So this will be 45 degree. This will be 45 degree. So the component of the G along the this one will be equal to along the plate will be equal to, this is 45 degree. So G along this one will be equal to G cos 45 and this will be G sin 45. So in this case, we have to calculate the Rayleigh number again. It's equal to, instead of G, it will be G cos 45. So it will be 0.70 times G. So we multiply 0.707 with the Rayleigh number. That is 1.16 into 10 power 5. 1.16 into 10 power 5, that will be equal to 8.2 into 10 power 4. That is the Rayleigh number. And the Nusselt number will be equal to 0.68 plus the new Rayleigh number raised to 1 by 4 into 0.514 equal to 9.4. Therefore, the heat transfer coefficient will be equal to the Nusselt number divided by delta T into H divided by K. So the value will be equal to say 6.1. The same the component that the same ratio so the Nusselt number as the Rayleigh number as well as the Nusselt number decreases proportionately with respect to the not proportionately the second component, this particular component will be proportionately decreasing with respect to the Rayleigh number. So when we substitute the Rayleigh Nusselt number, so the new heat transfer coefficient will be H per 6.1 watt per meter square. Therefore, the new heat transfer rate will be equal to H power into 2 into the sides will be H into T minus T infinitive. Both this distance. So if you take a unit distance in this direction, both the sides of this plate will be participating in natural convection. So by the same argument, the new heat transfer coefficient, the new heat transfer will be 9.77 watt per meter. So it has reduced slightly from the vertical plates because of the reduction in the natural convection that might happen because of the inclination, the tilt. So by that logic, the minimum heat transfer that might occur will be due to the minimum heat transfer that might occur will be due to orientation that will be of a horizontal plate. So if the orientation of the plate is vertical, you can expect a higher heat transfer coefficient due to the natural convection. But when we tilt it completely down to the horizontal position, the heat transfer from the top will be significant, but the heat transfer from the bottom side will be less significant because the higher temperature might be higher temperature surface will be on the bottom side of the plate will be transferring heat to the cold fluid. So the air which is hot will be remaining close to the lower side of the plate, while the higher side, lower temperature cold air will be at a lower side. So what I meant to say is that so if you tilt the plate completely horizontally, so the top side there will be significant heat transfer because this will be at a higher temperature compared to the ambient. So there will be natural convection. But in the case of bottom side, this surface will be at a higher temperature compared to the away from the wall. So the higher hot air and dense air will remain closer nearby the surface, but the lower far away from the one and far at a height at a distance very much away from the surface. Below the plate, it will be cold air. But since the dense towards the side, to denser air is a colder air and lighter air is a hot air. So lighter air keep on forming layers nearby the plate, resulting in a stratification and resulting in a poorer natural convection, and more the conduction dominates in that case. Because of the formation of a natural convection, the total heat transfer rate will be very much less compared to that of a vertical plate due to the natural convection. So the best heat transfer coefficient. So what we could say is that the best heat transfer orientation is vertical, and the worst is the horizontal one by the same argument for the natural convection basic flow. That completes the session for this week. So in this session we have seen a doubt that is being cleared regarding the momentum thickness, and we have seen 3 questions based on natural convection. One is an integral solution for based on a temperature and velocity profile, and the second one is a numerical problem to calculate the heat transfer to calculate the temperature of the surface. If you know the heat transfer coefficient, we have seen the concept of the flux Rayleigh number, And third one is a constant wall temperature case, but dealing with the different orientation of the wall, vertical to slightly inclined to the horizontal, and we have seen which is the vertical is the best heat transfer heat transferring orientation for the plate. So that's all for this session. If you have any doubt, you can post in the course website. We can meet next week with the further with the free convection in the tubes, internal free convection cases. That's all for the session. Thank you.